Osborne, and I serve as the Dean for the College of Science and Health Professions. And it is a pleasure to welcome you to the Science Building today. We're happy that everyone will come. And I also, I've never done this before, but I have the pleasure of introducing our next speaker. And that is the 19th President of NSU, Dr. Steve Turner. And he's going to share with us about LP Woods and the importance of having the Endowed lectureships. So Dr. Turner.
Thank you. Good afternoon, all. It's great to be with you. You know, I really feel like I'm speaking about one of the true who's who of Northeastern State. I can tell you that, honestly, I did not know much about LP Woods until we, Dr. Landry and I and the others on the Veterans Monument Committee started digging into that history of NSU and specifically World War I and forward. And if you, suddenly you start going back and you say, okay, we all know that shots heard around the world, we know what started, and the first pandemic in 1918, and then suddenly out of the blue you see the name of LP Woods appear in 1921. And a math professor. What I can tell, and someone here can correct me, is that he was educated in Columbia, but also at the University of Texas. I'm not sure where he got his undergraduate degree, but a very interesting person. So not only do we see him as a faculty member, again, we became a public institution on March 6, 1909, and this is someone that's hired basically 12 years later. So he and Dr. Hackler and some of those names that you hear through time are those, again, some of the who's who. I'm also reminded every day as I pull out my drive about LP Woods, because there's two houses that the institution owns. One is the Roseman House, which was named and built by Gideon Morgan, who was the construction superintendent of Seminary Hall. That was his home. It was also the hospital, Tahlequah City Hospital for a while. Very interesting. The other is the LP Woods House, which, Peggy, I don't remember what year it is, but we were there with Isabel Baker when we had the Woods family, and we dedicated it as the Center for Women's Studies. So every day I think about a little bit, as I leave the drive, I think about that. But let me go very quickly. This is impressive when I think about LP Woods. So came here as a professor of math in 1921. In 1922, he was moved from the math program. He traded places with J.M. Hackler to head up the officer training program. Now, there's a couple of bookends in his life, and I'm going to jump ahead because here we have 1922, and interestingly, in 1945, he was one of about 4 faculty selected to create a new 2-year radar program for the Navy at Northeastern. So he's in an officer training program in 21, and did you hear what I just said? In 1945, he's still having a positive effect on military people, saving lives through appropriate training. And history records that great things happen because of his work. We know that he went back and forth. There was a little bit of exchange, went to the psychology program, and then in 1923 or 1929, he was named the advisor to men, or the dean of men. So we just kind of watch him go, and then he went around. There were some problems in the residence halls, and that one, of course, as you know, Wilson Hall, and went blank on our first governor. Haskell Hall, thank you. I'm getting old, forgetful. Haskell Hall. So he actually got together and out of his love of students and created a lounge for men and a lounge for women in the administration building. Thus, Seminary Hall, because that was the administration. If you talk to people before the the building, which was the original student center, opened in 1958. If you say the administration building, they think of Seminary Hall. So he, as the dean of students, wanted, and he created lounge, and it actually solved some problems. Then we find in the spring of 1942, we know what happened on December 7th, 1941, he created a curriculum and went around and all of the special requirements to make sure that all the new male students coming in understood the requirements for the Army and the Navy, what was expected. Single-handedly. From that, he was asked by the Chancellor of Higher Education to come in with a group of about 5 others, and they created a statewide platform or curriculum that met the needs of students during and post-war, met the student needs. So obviously this is a person that was recognized as a leader in student needs and certainly very effective in wartime. In 1944, I mentioned he became one of the 3 faculty, I think, teaching in a 2-year radar program. In 1945, because of his background at Columbia, he created our first student orientation. And by the way, Dr. Freeman, it lasted a week. It was a week long, and it was really to help because students were not staying. They were dropping in and stopping out. And they wanted an orientation program to bridge what it had been like in their school to today. We see then, unfortunately, in 1957, October of 1957, he has to resign and retire due to failing health. In February of 1958, he succumbs to cancer. So when I say we're here today to talk about one of the who's of Northeastern State, we are. And in fact, I think the bigger question is with Professor Corkendall, these are big, he had big shoes to fill, and you're going to have to answer the question about how big is big. I think the other thing that we have to ask ourselves that we would not be here today, first, without the impact of Professor L.B. Woods. Secondly, we wouldn't be here today without his son and daughter-in-law, L.P. Jr., daughter-in-law Ann, creating and giving money that was matched by the state of Oklahoma. They gave money in 1999 to create a lectureship to recognize his contributions. And Dr. Hathaway said I should mention that, and that's true, because at that time, your money got doubled. When people gave, it was doubled. Now, that program has been eliminated. We still have endowed professors, but it's no longer matched by the state. So, to conclude, what better way to celebrate a life than for someone that never met you, someone that's stammering and stuttering, to talk about how important your life was. And in fact, his life touched my life. I got closer to L.P. Woods really because of the Veterans Monument. So now you know a little more, maybe not the rest of the story because I don't have time to tell you the rest of the story. But I say this, the craft of teaching, the role of a faculty member changes lives for generations. And I hope today we come away first with the answer of how big is big, but secondly, recognizing that we are here to celebrate the life of a big person in the history of NSU, Professor L.B. Woods. Thank you, Dr. Hathaway. Thank you for allowing me to be here. Did I do okay?
Yes.
Okay. He was talking.
Yeah.
He's got another important.
Well, I guess I should have also said before I introduced President Turner is that I also want to recognize and thank the leadership of Dr. Hazenauer and also Dr. Parrott, along with, Peggy Glenn for the foundation and putting this all together. Richard, I've had numerous conversations about wanting to do something like this and utilizing those funds for what they were meant for. And so, then COVID happened, right? And so I'm glad glad that we're finally getting to that point. So here to introduce Dr. Jim Kopinol is Dr. Richard Hazenauer, math faculty here in the department. Thank you, sir.
Well, thank you, President Turner and Dr. Hatcher for coming and giving some nice words and giving us some information about LP Mills. That was fantastic. Thank you, Peggy, for really making this kind of come together. This wouldn't be possible without Peggy Glenn and her staff, for sure. So, and Dr. Hathorn and Dr. Barrett and Dr. Ruby for encouraging us to keep going and trying to make this happen. So I met Dr. Quicknell in 2006 when I was a graduate student at North Dakota State. And after a few years, decided to ask him to be my PhD advisor. And I graduated with my PhD in 2012. It's starting to get harder to remember those things. And I guess I'm kind of the graduate student that never went away. So I have stayed in touch with him ever since then. I think I'm one of 14 graduate students that you have advised, and currently you're advising 9 or 10? 9 students. So you talked about the importance of education. I think math is probably kind of the embodiment to me of education, because we don't get to talk about cool stuff in the grocery store. We don't get to talk about our cool stuff with, relative strangers, because we don't use the same language, right? We don't use the same vocabulary. So I always joke with like my complex analysis class that this class is for me, because I get to talk about stuff I want to talk about, versus, everyday stuff, which is also fun. So with that, thank you for agreeing to come to tell me, and maybe you can tell us how big this is.
Well, I can't. That's the whole point. Yeah, so thank you all for inviting me. It is truly an honor to be here. This is actually probably about the third time that I have visited this campus, and I always love coming back. The motivation for this talk is sort of technology, and I don't want to scare you talking like the Unabomber or something like that. I am certainly not opposed to technology, but calculators make things easier, and of course now we've got computer software and this kind of thing. How many of you have ever just played around with calculators, just monkeyed around, right? An old scientific calculator. My dad was an architect. When I was a kid, I used to go in and I'd play with the calculator and stuff like that. And of course, in scientific notation, when they write, 1.7 times 10 to the 19, this seems very tame, right? You need a 1 and a 7 and a 19 and you're done. So I'm going to start off with kind of a fairly simple example. So this is my rendition of a chessboard, or as we call it in South Carolina, checkerboard. And I'm going to play the following game. I'm going to take checkers, right? My brother and I used to play checkers all the time. We'll say quarter-inch tall checkers. And I am going to stack 2 checkers here. I am going to stack 4 checkers here. 8 checkers here, doubling as I go down, right? So I double my stack every time. And so when I get down to the lower right checkerboard square, I have stacked 2 to the 64th checkers, quarter-inch apiece. Now this is a number that will easily fit into a scientific calculator, right? My question is, at a quarter-inch apiece, how tall is that stack of checkers? Somebody ballpark me. Come on, let's be interactive here. How tall is it? Empire State Building? Yes.
Well, I said the quarter inch, then 4 inch, and 2 to 64 divided by 4 is 2 to 62.
Right. A lot of inches, but how many inches is that, right? I mean, somebody ballpark. Empire State Building, that tall?
3 miles.
3 miles. Right. That's 3 miles, it's checkers, that's a lot of checkers. Okay, let's not embarrass me here. All the way to the moon. Beyond the pale, right? What do you think? Before I can answer this question, I have to explain to you what a light year is. Does anybody know what a light year is? It is how far a beam of light travels if you let it go for 1 year. Now, in 1 second, a beam of light will go 186,000 miles, 7.5 times around the Earth at the equator. Now, let that go for a year, that's a long way. As a bit of comparison, we are 8 light minutes from the sun. That's 93 million miles away. So if the sun blew up right now, we got 8 minutes to party down before it's all over, okay? That stack of checkers right here is approximately 12.4 light years tall. So it will reach, excluding the sun, to the nearest star and back, and then back again. So if you stacked it vertically and stood at the top of the flashlight, it would take 12.4 years for the beam of light to get to the bottom of that stack of checkers. Right? That's not intuitive. Now I'm going to up the voltage on it. How many of you have seen this notation here before? Some of you maybe. You've seen this? Like, for example, this does not mean 5, it means, this is a nice notation. The factorial comes up a lot in applications and so forth. So 10 factorial, 10 times 9 times 8 times 7, all the way down to 1. Let's play the game again. One checker, which was less than the first time around. 2 checkers, 6 checkers, all the way down. 64 factorial checkers. And let me give you some perspective here. I remember when I was a kid playing with my dad's calculator, 69 was a magic number on his calculator for the following reason. If you put in 69 factorial, it would give you an answer, something times 10 to the 98th power. If you put in 70 factorial, it would give you an error, because back then those calculators couldn't do anything at 10 to the 100th power or above, right? And so this would fit on my dad's calculator from the 1970s, right? Question, quarter inch apiece. How tall is that stack of checkers? Shorter or longer than 3? Longer. Probably longer, I wouldn't have brought it up, right? How much longer? Well, this one is actually quite a bit longer. How many of you all are familiar with the Andromeda Galaxy? Right? You've seen it, right? It looks like a fried egg. It's like Utah. You've seen pictures, right? The Andromeda Galaxy is a very long way away. It's actually 2.5 million light years away. But it's so big, it's about half the size of the full moon in the sky. It's just too faint to see with the naked eye. The Andromeda Galaxy, a round trip, the Andromeda Galaxy and back, is about 5 million light years. So 5 million light years right round trip. This stack of checkers will reach the Andromeda Galaxy and back 17 billion times. That's actually, there's not enough subatomic particles in the universe to create that stack of checkers, right? We don't have enough material in the universe. That is another very large number. Okay, let me give you something a little tamer. How many of you have ever played with one of these before? Rubik's Cube, right there, a lot of fun. This one has seen better days. It's unsolvable, I think, because all the colors, I can't even tell what they are anymore. But when I first went up to North Dakota State, I taught governor's school over the summer in governor's school. They were bringing these talented high school kids, and I needed to do something with them, and I taught them some abstract algebra using a Rubik's Cube as a teaching tool because there's lots of neat math on it, lots of symmetry on it. You could not find a Rubik's Cube in Fargo, North Dakota when I did this. And I always found this interesting because I went into my favorite toy store and I ordered. They said, how many do you want? I said, 25. And they, what? But anyway, so they ordered 25 Rubik's Cubes for me. 1 month later, every toy store and gas station in Fargo, North Dakota had Rubik's Cubes in it. So, there was something going on there. But anyway, when I got the box, they all came in this little box, and it said, billions of combinations, only one solution. This to me is the great missed opportunity in advertising, right? I mean, right, isn't that what you're supposed to do when you advertise? You tell someone how great it is, you exaggerate. I mean, my car is like a McDonald's dumpster with an engine in it, right? But the dealer told me how great it was, This is a great missed opportunity. How many combinations are there on this? Well, and I mean without cheating, so you don't take a screwdriver and pull it apart, just how many combinations can you get from just messing around with it? It is approximately that many combinations. Now, that's a pretty tame looking number, right, on the Rubik's Cube, right? You need a 4, a 3, and a 19, right, to describe that in scientific notation. 43 quintillion, something like this. How big is that number really? And by the way, let me kind of take a quick segue and say, none of what I'm talking about, except maybe something at the very end, requires any particular expertise to do. You can all figure this stuff out on a calculator, but very easily. It's actually kind of fun. So, let me give you some perspective on this. I'm not going to get the population exactly right, but the population of the United States, we'll assume, is 300 million people, right? If you take a Rubik's Cube and give it to every human being, man, woman, child, in the United States, and say, go. And they start scrambling the cube. Every one of these 300 million people get a different combination on the cube every second. And we've got a big computer that records this all, right? So you got 300 million people, each getting a new combination on the cube every second. Nobody repeats what anybody else has done. They're all getting something unique every second. And you let this process go 24 hours a day, 7 days a week, for 40 years. And the computer is just recording all the combinations you've got. At the end of that time, you will have accumulated about 0.8% of the number of combinations on the cube, right? That's kind of like a little inside thing about math, because you ain't going to get lucky and solve this thing. You got to know something. You got to know something about mathematics or symmetries or geometry or something to be able to solve this. You're not going to guess it, right? Okay. Any questions so far? Okay, I've got another little anecdote. How many of you know what? I know in the old days I would get different answers for this if I asked this question. How many of you know what a Google is? I know you know. But of course everybody thinks that I'm talking about the website where you look up stuff, right? How many of you know what this is? Now, this is a name that was given to this number. 10 to the 100 power. This is the number that would have made my dad's 1970 scientific calculator blow up. It couldn't handle 10 to the 100 power or higher. And this is often called a Google. So, when I was in Fargo, I had a friend, and she was big into books, and she had a couple of kids, and she was always really good about giving her kids books and stuff. And she had this book that she gave to her kids and it brought up the term Google, 10 to the 100th power. How big is this? And I read the book, and it was a great book, but they explained to Google, as the author said, that he had talked about this in public audiences like this, and he explained to Google, how big is that? It is more than the number of raindrops that have fallen in Scotland in the past century. And when I read this, I laughed. And, you know, my friend said, well, what are you laughing about? I said, the author is assuredly correct, but it is a great missed opportunity. So, being the kind of guy I am, I decided to figure out what's going on with this Google thing. So, I did some computations. Suppose that Scotland is 32,400 square miles. And actually, because I wanted to make my bet safe, that's actually a little bit bigger. By the way, anybody know why? It's actually 31,000 and some change. Anybody know why I made 32,400? Why did I come up with that number? The correct answer is I am a lazy, lazy man, and that number is a perfect square, right? And it made my life a little bit easier. So this is actually bigger than Scotland. Well then, I said, well, let's go crazy with this. Now, this is the embarrassing part of the story, because at this point I was kind of guessing. I assumed, what's a torrential rain? I thought to myself, how many? And I thought about sitting in the rain and whatever. I said, how about this? I'll say that a torrential rain is 200 raindrops per square inch per second. Turns out I was a little off on that. I did some reading around. Some meteorologists classify torrential rain as 113 drops per square foot per second. So really, I'm up by a factor of like 288, right? So this isn't a torrential rainfall. This is God pointing a fire hose at Scotland, and just that's what this rainfall is. All right. So here's the question: at my ridiculous estimate of 200 raindrops per square inch per second over 32,400 square miles, which is too big of Scotland, how long will it take before a Google of raindrops falls? Anybody want to guess that one? Yes, it's a lot actually. And it's funny, it's the same number of billions. We'll assume here, for the purposes of this talk, that the universe is 14 billion years old. Right? That's the standard age given. The amount of time it takes Google raindrops to fall on Scotland at this torrential rate is 870 billion times the age of the universe. So a century was a bit of an underestimate. So, okay. Any questions? Okay. I'm sorry.
How many billion? How many times did you say billion?
How many times? I said 7 times. Right. So it's like 8.7 times 10 to the 65th, something like that, times the age of the universe. Okay. If I and my sources all counted right, oh, I got to take a little risk here. I'm going to do the birthday problem. How many of you have ever heard of the birthday problem in folklore? We're going to test it here because I'm a brave person. There are, by my count, I think we've got up to 34 people in this room, right? Now, I'm going to be a little bit unrealistic because I'm going to assume that February 29th doesn't exist. I'll just make it easy. Does anybody get born on February 29th? Chance? It's not that common an occurrence. So there's 34 of you in the room. There's 365 days in the year. What do you suppose the chances are that at least two of you have the same birthday?
90.8%.
What's that?
90.8%.
That's a little over.
Oh.
Most lay people would say it's much lower than that, right? Because really, what do you got? 34 chances out of 365 doesn't sound very promising. I can't guarantee it, but I've also got something else in my favor. Y'all feel brave enough to try it here? We've only got 34 people. Let's try it. What I'm going to do is I am going to point people. Now you got to speak up so people in the room can hear you. If somebody hears their birthday, and I just mean day and month, I don't mean year. If somebody hears their birthday, just yell at me and we'll stop it. Okay?
August 13th.
July 3rd.
22nd,
Well, which,
September 22nd,
okay.
February 20th,
23rd.
March 12th,
August 30th.
May 5th.
Ah, that's mine.
Actually, believe it or not, there was a 79.5% chance that that was going to happen. And it's actually better than that. Because the assumption that I made in making up this table is that all birthdays are equally probable, which is not true. There are more people born 9 months after Christmas, 9 months after Valentine's Day. My birthday happens to be September 16th, which is the most common birthday in the United States, as a matter of fact. So they're not distributed equally, so that shifts the odds a little bit more in my favor. But this is surprising, isn't it? That with just 34 of you in here, there's almost an 80% chance that I'm going to double up. The reason for this is kind of subtle. Because what I said was at least two of them have the same birthday. This incorporates a lot of possibilities, right? Maybe you two have the same birthday and you two have a different same birthday. Maybe you three have the same birthday, you have the same birthday. There's all kinds of things that can happen that would make this work out. So how do you figure out what the chances are? And I'm not going to go through anything super deep. But I'm going to show you something that will illustrate a bigger scale for my next little demonstration. This is how the birthday problem sort of works. The first thing you got to do is you got to think sort of around my question. What I asked is, what are the chances that at least two of you have the same birthday? Well, how do I lose? If I tell you all, okay, I think that at least two of you have the same birthday, what's the only thing that can happen that'll screw things up for me? Nobody in the room has the same birthday. That's right. Everybody's got to have a different birthday. So think about this as a room. There's 34 of you. So when I put the first person, I need to give them a sandwich, but when I put the first person in the room, what are the chances that that person has the unique birthday in the room? 100%, because there's nobody else in the room. Okay, let's bring in the second person. How do they both have different birthdays? Well, this person's just got to dodge this person's birthday, right? And what are the chances that that happens? Well, this person needs 364 chances out of 365. Bring the third person. How do we keep my screw up going? Well, this person has to have different birthdays than both these two. Bring in the next person, has to dodge the birthdays of the first three. And these numbers are very close to 1, right? 0.99 something, like that. But if you've ever played the calculator what happens when you multiply numbers that are less than 1, or when you start taking powers of it, right? What happens when you take 0.9, 90%? What happens when you square that, multiply by itself? You've already dropped to 0.81, right? What happens when you cube it? You've already dropped to 0.729, right? Do it again, 0.6561. It drops actually pretty fast. Now, these numbers are closer to 1 than 0.9, but they do pick up momentum, right? So the answer should be so you can do this calculation yourself. And what do we have? 34 people in the room. So I guess if we could put 331 or 365, and maybe that number's not right, maybe it's 330 or something like that. But when you multiply this number, you're multiplying this, you're basically taking the 34th power of, it's actually smaller than this, 34th power of this thing, and you will find that this number has shrunk. In fact, in this case, it will have shrunk down to about 0.195, no, about 0.25, or 0.025, that is. And so this will give you about 79.5% chance, right? Now, does everybody kind of understand what we're doing here, right? Because the only way, the way I'm right is this has, or the way I'm wrong, this has to happen. The way I'm right, it's 100% minus that. Everybody cool with that? Now, I want to up the voltage a little bit, and I'm going to ask you a problem that is probably the most intuitive problem that I have posed, and so you shouldn't be afraid to answer this. Suppose I cut a cube and my cube is going to be very big. So let us have a little suspension of disbelief and assume that this is a medium for Flat Earth Society. I am going to assume that the Earth is flat when I pull the cube out. My cube will extend from here to where I came from, Clemson. That's roughly 648 miles. As the crow flies, not on the road. Right? So, from here to Clemson will be the edges of my hole. It's going to be 648 miles by 648 miles by 648 miles deep. Right? Big old hole. I am going to fill this hole with 1 cubic inch squares, or cubes. I'm going to fill this up with 1 cubic inch cubes. There's a lot of them that go in there. Everybody agree with that? Lots and lots of 1 cubic inch cubes that I can fit in this 648 by 648, 648 hole. All of these cubes will be white, with one exception. Now, one of them's painted red. Okay? So, I've dumped all these cubes into this hole. It's full up, all white except for one red. Something. I put a blindfold on you, and I'll let you pick a cube out at random. Any one you want. What is the probability that you pick the red? Just ballpark me here. How about this? Very low, right? Very, very low. Not 0, because you could certainly get super lucky, right? But there's a much bigger chance of a tornado blowing through a junkyard assembling a jumbo jet than you picking that red cube out of the ground. Are we all on the same page? Picking the red cube, very low probability. So keep that in mind. Now, let me ask you this. Low probability. Agree on that. Now, I'm going to ask you a different problem. And my different problem goes something like this. Suppose that I take, how much? I'm going to take 1 mole. Any of you chemists, right? Anybody take a chemistry class? I'm gonna take one mole, which is chemistry thing. Let me put that in perspective. About 3/40ths of a cup, or about 3/5 of an ounce. So I'm gonna take a little vial, about 3/5 of an ounce of ink in it, and I'm gonna dump it into the Pacific Ocean, right? And I'm gonna let things mix. I'm gonna assume that the ink mixes into the oceans completely all over the world, right? And so not just the Pacific, but all the oceans, it mixes everywhere. 10 years later, I go and take a vial of the same volume that held the ink that I dumped in, and I dip it in the ocean and pull it out. What is the probability that at least one of those ink molecules that I poured into the ocean 10 years before is in that vial? I'll give you a hint. At least one. I don't know if that's a technical chemistry term or not, but I'm going to call it an ink molecule. When I go back and dip that same vial in there 10 years later, after it's thoroughly mixed in the ocean, what are the chances? Well, here's my hint. The proportion of ink to ocean, that is, the molecules of ink that I dumped in there 10 years ago, if you take that number and you take that to the proportion of water molecules in the ocean, that's about the same as this proportion. Red cube to white cube. So the density of the ink molecules in the ocean is at the same proportion of that one red 1 cubic inch cube in that big 648 by 648 by 648 mile hole. The proportion's the same. What's the chances that if I dip in there that I'm going to get at least one of those? Anybody want to take a flyer on that?
Is the ink soluble?
I'm a mathematician, but this is theory. Yeah. We will win. The assumptions in the problem are ink molecules are always ink molecules. They don't dissolve or anything. They keep their integrity. If you like, imagine them as little blips or whatever. No proton decay, no tunneling, none of this stuff.
Just checking.
So, the way to figure this out is the same principle as birthday. So let me kind of lay this out for you a little bit. Let's let in, and I'm going to use just the letters later. This is going to be and I bet you know what that is. This is Avogadro's number, right? This is the amount of, this is the number of molecules of ink that I originally let capital N be 46. This is the number of water molecules in the ocean, roughly. So, think of it just like we thought of the birthday problem. How do I get a vial that is pristine in the sense that there are no ink molecules, none whatsoever? Well, to have this happen, just think about adding the molecules one at a time. This is more of a daunting task because I've got to do it 6.02 times 10 to the 23rd times. But nonetheless, in principle, I could do it. What is the chance that that first molecule is a water molecule? It's really good, right? Because there's lots and lots more water molecules than there are ink molecules. And so the probability is basically N, old ocean, number of molecules, new ocean, I've added the ink, right? So I've got that many chances out of, and this is minuscule compared to, this is almost one, but a little bit less. Well, now I've got one less water molecule. And now I've got two less water molecules. And just do this 6.02 times 10 to the 23rd times, right? Which is, that actually brings up another question. How do you even do this, right? Because actually multiplying this out, if you could do 93 quadrillion calculations per second, it would take about 75 days to compute that product that I write out. If I continue this 6.02 times 10 to the 23rd times, at 93 quadrillion calculations per second, it'll take 75 days to compute this number. But what we can do is we can, instead of this, we can approximate this way. And my inequality is correct. And this, there are techniques to figure out what this number is. And actually I did it a couple of ways. By the way, these are all huge numbers. How would you compute this? This is another great application of logarithms. Because when you take the logarithm, you still got huge, but you can bring the exponent down. And that really taking a huge power of this number here, it's much easier to multiply a huge number by something else, right? And so, I did this computation, and it's just like the workday problem. If I multiply this out and call this P for product, these numbers are very near, well, these numbers are all very near 1. These ones are getting smaller. This one is less than 1, and I'm just taking large power of it. But, again, I multiplied it by itself a load of times. And that brings things down, and in fact, what I got at the end of the day was that there is at least one ink molecule we'll say, I'll do this in terms of percent chance. Now remember, the percent chance of getting on the first one, on the second one, you're almost exclusively going to be getting water molecules because there's so many more water molecules. But you've done this so many times. And if you're interested in this, I'm happy to hang around after the talk and go through some details about this. It is conservatively, because actually I play this very conservative. It is almost a done deal that there will be at least one ink molecule in that vial, because taking that high power there really brings that power, it's almost zero. In fact, when you multiply that out, it's basically 0.0003. Right? Now, think about that the next time you're sharing a swimming pool with some kid wearing a diaper, right? I mean, that's a little disturbing. Okay, I'm going to give you one last thing to go on. And this is, I'll leave this as an exercise. And again, I can't focus. You might wonder why I started 3 here. That's just to make sure that these terms are all positive. This is actually, if you add this up forever, you will get infinity. As some of you may have seen adding up things infinitely often. You might have even seen this, some high schools believe it. Anybody know what that adds up to? 1/2 plus 1/4 plus 1/8 plus 1/16 forever. This is 1/2 just by itself. Now to 3/4, 7/8, 15/16. Then I get 31 32s, 63 64s. Anybody? What should this add up to? Good, good. On the other hand, that adds up to infinity because it just keeps getting bigger. This is exactly what happens. This adds up to infinity. And what I mean by that is very imprecise. No matter how big of a number you pick, I can add up enough terms of capacity. But this is fine. Now, what if you add up the first, this is 10 to the Google power, right? So this is 1 followed by a Google of zeros. There is not enough material in the universe to write this in standard form. In fact, there is probably, depends on who you talk to, physics, somewhere between 10 to the 80th, 10 to the 87 subatomic particles in the universe. You would need 10 to the 100 zeros to write this out in standard form. So you can't write this number out standard. You can't do it. There's not enough material in the universe. That's how many terms I'm going to add up. Now, my hint is this adds up to infinity in the sense that it gets as big as you want. And I'll give you another hint. The first term of this, the first term that goes into that, when you plug in n equals 3, is 3.22. So this is 3.22. The second term is about 0.5. And the second term is 0.26. And then the rest, lots of others. What does this add up to? This adds up to about 10.1. The first term is 3, you're almost there, but it takes that many terms just to reach 10.1. That's another kind of powerful argument with math, because almost any computer would be fooled by this, because it grows to infinity, but it does it so slowly, it's essentially infinite. Okay, I won't keep y'all anymore. Questions? So do you know how big big is now? Well, that's the right answer.
I think mine's a little broken.
Well, that's it. That's kind of the point, isn't it, right? Because we take these numbers as output from computers, calculators, whatever it is, and we can write it in very convenient representations. But when you really try to understand what's going on besides these numbers, it's very unclear. There was a famous mathematician, Jean Dubonnet, and I remember him saying, you know, because everybody picks on math and being abstract, he said, 2 and 3, I understand these numbers, even 10,000 is getting a little abstract, right? And there's a certain amount of truth in that.
The question is, that expression, is that natural log of n, natural log of natural log of n, or?
Yeah, let me clarify that. Yeah, so 3 terms, natural log of n, natural log of n. It's just the product of those 3. Yes?
So back to your white cubes and your one red cube, what was the final answer there?
Well, so the probability of picking one red cube out of that, you know, thing, the probability is not 0, but essentially 0, right? But if I mix an Avogadro's number of those ink molecules into the ocean, then when you've got that mixed in, the proportion of ink molecules to water molecules is essentially the same as the red cube to the white cubes in that big hole I dug, right? So it's distributed the same there. But the chances of getting at least one ink molecule back, it's almost a done deal, right? And the difference is you're doing the experiment so many times that it's hard to do. It's easy to dodge it a few times, but over the long scale, and that's surprising, right? It's not intuitive.